Aí, melhorou? Pronto. Problemas técnicos resolvidos. Agradeço também o pessoal aqui do Grupo PET por ter organizado, então, toda a logística dessa apresentação. Tá? Vou agradecer também François. François, merci beaucoup d'être venu. C'est un grand plaisir de te recevoir ici parmi nous et pouvoir partager un peu de son savoir-faire ici avec nos étudiants. Merci beaucoup. Então, a palestra do François, então, ela vai ser nominada Analog is Not Dead, mas antes disso eu gostaria de apresentar para vocês um pouco a biografia, então, do nosso convidado. Então, o François, ele, em 2005, ele obteve, então, o mestrado dele na Universidade de Bordeaux. Logo na sequência, ele começou, então, o seu doutorado, que ele, então, terminou no ano de 2009. Tá? O François, tive a oportunidade de trabalhar com o François durante todos esses anos lá em Bordeaux, onde eu fiz, então, também o meu doutorado. O François, então, ele é membro hoje do CNRS, que é o equivalente nosso aqui do CNPq, tá? Que é a instituição de pesquisa lá da França. Ele trabalha, então, principalmente no design de arquiteturas radiofrequência. Tá? Ele desenvolveu, então, um sistema que serve a substituir as cadeias de recepção de telefones celulares, por exemplo, tá? Que chama-se SASP, Sampled Analog Signal Processing. Tá? Foi a primeira vez no mundo que foi demonstrado que é possível, que o princípio do software radio ele é possível e que é possível estar recebendo ali vários standards de telefonia celular dentro de um só receptor. Tá? Então foi um dos primeiros, pode dizer mesmo, o primeiro que conseguiu fazer isso demonstrando em um circuito em silício. Tá? Ele faz parte também do grupo comum entre a ST Microeletrônica e o laboratório IMS, que é um laboratório comum entre a indústria e a universidade, muito comum na Europa. Tá? E em 2010, então, ele foi um dos cofundadores de uma empresa chamada Atlantic Innovation, tá? Que trabalha na parte de inovação, na parte de eletrônica, sistemas embarcados e circuitos integrados. Então, vou passar agora a palavra para o François, que vai proferir então essa palestra para a gente. François.
Thank you. Desculpa, não falo português, mas falo inglês. So thank you very much for your welcome here at Curitiba. So I'm going to talk today about analog, because here I know that you are the king of digital. So I'm going to create a debate about analog, and I want to say that analog is not dead. So I'm coming from IMS laboratory at Bordeaux in France, and as we are at Bordeaux, you can see that the laboratory and the university is very close to the vineyards, and it is the Haut-Brion vineyard, the best wine in the world. So we work at only 50 meters from those vineyards. Great place to work. So the IMS laboratory is a laboratory which works around integrated circuits. So we work on modeling, integrations, design, and everything around reliability. And we had the great honor to be labeled as the Integrated Circuit Reference Lab in 2010 by the French Evaluation Agency. So we are a little bit more than 120 tenured researchers, and there are more than 130 PhD students. And I guess more than 20 of them are Brazilian. So my talk today is going to introduce what is microelectronics. So first, I'll talk about how we make an integrated circuit, and I'll introduce the debate about analog versus digital. Then I'll talk about wireless technology, what is an RF spectrum, what is an RF transmitter, and I introduce the last part of the talk about software radio. So, microelectronics. Why are we doing microelectronics? You know all the components like resistor, capacitors, inductors, diode, transistor, and there is a guy in the 1960s who was able to integrate all those components in just one chip. Why integrated all of that? You just suppress, you just delete all the wires. What is a wire? A wire, it's resistive, it's inductive, it's capacitive. And when you have a resistor and a capacitor together, it makes a low-pass filter. So when you have a low-pass filter, you can't go very high in frequency. So if you delete all the wires. That means if you integrate all those components in a very, very small circuit, you suppress the resistive effect, the capacitive effect, and you can go very high in frequency. That's why your microprocessor in the computer can reach gigahertz frequency. And there is another guy called Gordon Moore who told us that every 18 months, roughly, we are able to double the number of transistors in one circuit. That means we divide by 2 the area of the circuit. And that also means we can go higher and higher in frequency. So if we want to go higher, we have to integrate, but the only drawback is the cost of the circuit. If you reduce the size, you have to pay more and more. So how we fabricate the circuits? This is a wafer. So on a wafer, it's silicon. We are going to print the circuits. So here on that wafer, which is quite big, we have more than 1,000 circuits. And a circuit, it's something very, very small. 1 millimeter square, maybe 2 or 3. And everything you can see in colors here are the resistors, the capacitors, the inductors, and of course the transistors. So if we reduce the size, we can still go higher in frequency. So this is the size of a transistor, and we can see here the smallest size about that circuit, which is a 90 nanometer. So this is very small, and here the screen is to compare with the air size. So we are very, very small compared to the air size. So nowadays we are able to make some circuitry around 20 nanometers, and the physical limit is around 10 nanometers. So let's talk about analog and digital. What is analog? Analog, just to say one word, it's continuous. Continuous in time, continuous in value. It's not discrete. What is discrete is digital. Digital is discrete in time. That means the signal is sampled, and it's discrete in value. So this is an example. For example, my voice through that microphone is continuous. I have a full dynamic range. My voice can go very low or very high, and the frequency is continuous. So I can create some function like to amplify a signal, which is a continuous function. Let's see what is a digital circuit. So you may recognize the 0 and the 1. You are clever about that. So you can create some functions with that. You have 2 levels, a low level and a high level, and you make some comparison, and you are able to say what is a 0, what is a 1. And when you have done that, you can create some figures. For example, here 5 is 101. So digital is good. It's easy and cheap to store. There is no noise. Always 0 and 1. You have an algebra, Boolean algebra, with some logic functions. And you can do some digital signal processing, which is very easy to implement. But the main drawback about digital is that when you convert a signal, it's always converted in a finite number of binary digits. For example, with 6 bytes, we have only 64 possible values. This is very limited to me. And we have some errors that can be introduced. Quantization errors. It's quite hard to control the gain, the offset, so that's not very accurate. So let's see how we come from an analog signal to a digital one. This is the analog, my favorite. So we sample in time the analog signal. So this is the first discretization. As we can see, we totally ignore what can happen between 2 samples. For me, there is a loss of information. And then we convert each values in that finite number. So we can lose some information about the accuracy of the signal. So maybe there is drawbacks and advantage between analog and digital. So Now I changed my mind. I'm going to talk about wireless technology. So this is a spectrum we can find in many countries in the world from 0 Hz till 300 gigahertz. It's full. All the space is used. You have your GSM or maybe UMTS, Wi-Fi, Bluetooth, everything about military, satellite, everything is addressed. But that spectrum, we can see that there are some space which are very used and some very large hole. It's not really used very often. So if it's not used, and I don't want to be in that space because I can't call, my GSM doesn't work because the network is crowded, I want to call that free space. So this is a topic we are going to deal today. And to understand it, let's talk about the data rate. 20 years ago, we just want to call with our cell phone, our cellular. Nowadays, we want to connect to the internet. We want to send pictures. We want to log in on the Facebook, just with that, the iPhone. We want to do so many things that the data rate must be really huge. And that's why we want to use a larger spectrum. So this is quite a sum up of the standards we can find nowadays. So the traditional GSM and DCS and PCS, which are the standards used in America. We have the UMTS for the video conference. We have for the local networks, the Bluetooth, the Wi-Fi also at 5 gigahertz. We have the WiMAX, which is coming, and maybe some future standards, we don't know, which are going to come in the next few years. So, as we can see here, each of it address one frequency with one modulus scheme and with a different bandwidth. So this is what you can find inside your cell phone. Your cell phone is done like that. There are several receiving chain and transmitting chain for each standard. That means in your cell phone, if you have an iPhone, for example, you can find maybe 10, 15 chips to address all the standards. It's a lot of space. It's a very high cost. I don't want to pay my iPhone $500. I don't know the price here in reals. 2,000 reals for an iPhone? Maybe 2,000. Okay. I don't want to pay that price. I want to pay a lower price. So the idea is to say why I need so much chain. I can just merge all that in one chip, and that chip is able to understand every standard from 0 to 5 gigahertz. So the price of that chip will be lower, of course, and I can reduce the power. Only one chip can reduce the power. That means that my iPhone, I have to charge at the end of the day. I just charge it at the end of the week. Wow. And of course, I can reduce the time to market. If there is a new standard, I don't have to call the telecommunication industry, just make me a new chip, I want it in my cell phone. No, I have the chip which is able to connect to everybody. So let's say this is the old world. Forget it. Old cell phones. So I am the customer. I am the king. I decide, like you are all the customers, what I want in my cell phone. And what I want is more and more functionalities in my cell phone. And at what price? Not at the same price, but at a lower price, of course. When I want it. Not in 2 years, not in 1 week, but not this afternoon, it's too late. Tomorrow morning, of course. And if I add some more functionalities, I don't want my cell phone to be bigger and bigger. I want it to be smaller and smaller, just to go in my hand. So this is the concept of software radio. That means that you have only one chip, very small, that can go in a cell phone and which is able to address every standard. But as you see software, that means that all that signal processing is going to be done digitally. So let's go if it's possible. or not? Let's go and see that. So this is you, the customers. So you want more functionalities. That means new applications, new standards at the same price or cheaper. You want it right now, of course, and you want it to be as compact as possible. This is me, the analog designer, and I can give you some answer how to do it. So I can say you that, oh no, only one chip can address only one standard. No, I don't want to think about new solutions, because each chip addresses specific frequencies, specific channel bandwidth, specific modulation type. And if you want a new standard, okay, I'm going to sell you a new chip. It takes time, of course, because I have to hire some engineers like you to work on it. Okay, and of course, I won't pay you so much. The money is for me. And if you want the real multimedia conversions, okay, we'll put all the chips together in a big phone. Okay, no, not for me. Not for me, because I want to address the software radio concept. And what is really the software radio concept? You have your antenna that receives all the RF signals from 0 to 5 gigahertz. And then, because you are here at Curitiba, you say, I just add an analog to digital converter. That means all those signals I converted into digital. I have my 0 and 1, and then I can do my digital signal processing. Let's say a microprocessor can do it. Okay. So I can sort with that signal processing the voice, the data, the localization, the three main things I want. So I just need a direct digitization after the antenna. That's a one-chip solution. And of course, it brings me flexibility and recompatibility brought by the DSP. A new standard is coming. Okay, I just upload the update in my DSP. Up, and it works. It's just an update because it's digital. Okay, so now this is the market, and the market says you have very strong standards to respect. The main one is the GSM. GSM claims for a 100 dB resolution. That means 16 bits for your ADC. And of course, if you want to sell your one chip solution, you have to address all the standards between 0 to 5 gigahertz. That includes GSM, Bluetooth, Wi-Fi, and the new standards in that frequency. So there is a guy called Shannon. You know Shannon? Shannon theorem. If I want to, Shannon theorem, Professor Mariano's student know it. Okay? So if I want to address the standard till 5 gigahertz, I have to sample it at least at twice that frequency. That means 10 gigahertz. So I have to find an ADC that converts the signal with a resolution of 16 bits, at least at 10 gigahertz. Do you think it's possible? Yes? No? We are going to see. So, this is a good game. It's quite hard to see. The blue stars on the right indicates where the ADC should be. So, what is in white? It's very easy to do, the ADC, to create it. You can find it in the market, downtown Curitiba, no problem. Very low price. But when you enter in the green or even in the red, it becomes difficult to create such an ADC. And in blue, it's difficult to or impossible to do it right now, because that ADC you want should consume at least 1 kilowatt to convert the signal. And 1 kilowatt, it's quite hard for a cell phone battery to have. 1 kilowatt, it's in your car maybe, but I don't want to have my car battery in my hand when I call someone. You too? That's fine? No, I don't want that. I want maybe a power consumption of 10 milliwatts, no more. And we can say that maybe in 15 years, we will be able to create that ADC. Okay, so the power consumption is the main problem. Now it's a yellow star. The power consumption is quite hard to be solved. But let's dream. I have solved that problem of power consumption. Even physics is against us. This is just a scheme to indicate our blue star, and this line here is the limit of the accuracy of conversion. Everything which is after, thanks to Heisenberg's theorem, say you are not sure what you are going to convert because of physics, electrons, things like that. So physics said it's impossible to have a 16-bit at 10 gigahertz ADC. It's research. We can go further that. Okay, so let's say, forget physics, forget power consumption. I have my ADC in my hand. That ADC, which is low power, which is against physics. Okay, let's see what's going to happen to the DSP after that. I am able to convert all that, but the DSP have to handle with more than 600 giga instruction per second. Do you think it's power hungry? It's very power hungry, more than 1 kilowatt. So it's not one car battery you need, it's all a parking lot. It's 10 cars, 100 cars. So very hard to connect my cell phone to 100 cars battery. Maybe to a nuclear power plant, I don't know. So this is not feasible at all. So our solution is to find new RF architectures to challenge that ADC technological bottleneck. So let's say if I'm not able to put my ADC as close as possible at the antenna, let's start as close as possible to the DSP. That means in baseband, where the frequency is low, where the resolution is low, everything is okay. So I try to work on digital on basic function which are baseband. That means the mixers and the IQ separation and the demodulation. This is quite easy to do, but that ADC still have some strong requirements because I am just after the mixer and the LNA, and I have to deal with a very high dynamic range and still quite a high frequency, which is low compared to the other one. So this is what we call software-defined radio. This is a limited architecture. Limited about what? About that mixer. That mixer, that means that you have very high frequency signal here, and here you have low frequency one. But this part limits you to very small, narrow band in the frequency scheme. That means that you can just address GSM, or you can address DCS, PCS, or Wi-Fi, but not at the same time, and maybe just one standard. But that's we call software-defined radio because we can process several channels in that bandwidth. That means that I can call with Claro, OI, or Team at the same time. Okay, so this is interesting too. So this is an intermediate solution. We have worked at the IMS laboratory. That was 6 years ago, I think, when Professor Mariano arrived there at Bordeaux. He proposed to create an ADC in intermediate frequency. Intermediate frequency is 1 gigahertz, quite high in frequency, 1 gigahertz with a very high resolution. And he offered a new architecture to challenge that. So he proposed a continuous time sigma delta modulator. So this is Chinese for us. Not Portuguese for me, not Francis for you. It's Chinese. But let's sum up that. This is a very, very good ADC, which is in the state of the art. And as I am here to introduce you to microelectronics, when we create a chip, we design all that chip. That means that we put all the resistors, the transistors in it, the capacitors, and we test it. This is a funny story I'm going to tell you. Because when you create a chip, it's a lot of work. It's 3 years, 4 years of work. So your chip is like your child. And when you have a child for birth, you give a name. Of course. And because you make some prototype, there is several versions. The first version is called A. The second one is called B. As we are very good in France, there is always A version. So the A is always at the end of the word, here. And Professor Mariano has to find a name to his chip. So the chip, he named it Ipanem, for Ipanema. there were no new chips. Otherwise, there should be a Copacabana. I don't know. Okay, so this is an intermediate frequency, intermediate solution. We are still not in the software radio. So let's see the huge step we have done about that. Okay, so I come back to my ideal solution. That means the antenna, the ADC, and everything is performed after into digital. We said it's still a dream. Because a dream for user, of course, because it's compliant and friendly for any RF product. I have my cell phone which is able to speak with everybody, of course. It's a dream for the industry. Very low cost, low time to market. I can sell it to everyone. I can make a lot of money. I am very rich. This is a nightmare now. Why? It's a nightmare because the DSP should handle with that multi-giga instruction per second with a very low power. It's a nightmare for the RF designer. Yes, we have that one chip solution. It solves every radio frequency problem. So I have lost my job. I have nothing to design more. I go to the beach. Let's finish. Okay. But it's not a nightmare for me. And of course, it's a nightmare for the ADC designers community because the whole pressure is on them because the conversion is the key. So let's see what is the ultimate software radio specification. So the dynamic range, as we have seen, must achieve 100 dB, at least with 17 bits, with a very high sampling rate, and of course with very highly linear and low power chip, maybe 1 to 10 milliwatts. This is very, very small. So as we are not able to do it into digital, and I come back to the beginning of my talk, when it's not feasible in digital, why not trying to come back to the analog world? And that's why we had the idea at the IMS laboratory at Bordeaux, not to go directly to work on the ADC, but to relax all the constraints on the ADC into analog. And we have designed an analog processor. It's not like your microprocessor, which is digital, but an analog processor, which is called sample analog signal processor, who is going to who is able to be software like a software radio chip, but who is able to choose the band you want to address to demodulate the signals. Okay? So that analog processor works with voltage samples. Remember, voltage samples, it's continuous in time. It's not discrete. There is no 0, no 1. I have directly the value. It's continuous. And of course, we are going to implement an algorithm. So this is quite boring. This is the evening. I don't want to disturb you because it's the end of the day. I won't tell you about the story of that chip. I won't tell you about the algorithm, how complex it can be. For me, it was 3 to 4 years of work. I don't have time to say it in 10 minutes, but I'm going to tell you a story. And that story is to introduce you to the integrated circuit design flow, how we make a circuitry. So you know that we give a name to the chip here. This is the bus. But after the bus, there are several steps. The first one is to have an ID. Okay, for me, that was the morning when I was taking the shower, I had the ID. Maybe for you it's in the car, I don't know. When I have the ID, I'm going to validate it in MATLAB. Everybody knows MATLAB? Yeah? Okay. So MATLAB can say if yes or no, it's a good ID. Once I have that, I want to create the architecture of the circuitry. So for that, I use the VHDL AMS language. And I can design my algorithm as close as possible as a structure I'm going to implement into analog. Once the simulation says it's okay in VHDL AMS, it means that the behavior is fine. I can design the schematic with the transistors, the resistors, the capacitors, with the technology I want to address. maybe 90 nanometer, 65 nanometer, 20 nanometer if you are really rich. Okay? Once I have the schematic, I have done the simulation, I respect my specification. It's always very important. I can design the circuit. That means the layout. It's me who is going to say that resistor is going to be to that transistor like that. The metal layers, all that. Okay? So I still perform some simulation and say, okay, now I am ready to fabricate that circuitry. Me, I can't. But I have to pay a company like ST Microelectronics, maybe the Seitec, the next few years, Intel, IBM, and say, okay, I'm going to sell you 1 millimeter square for your circuitry. What is the price for 1 millimeter square? 30,000 reals. One car. Yes? One good car? So, and it takes 3 months. So if I have made a mistake there, that means that my chip won't work. And the car you wanted to buy for next year, you forget it. Okay, just for 1 millimeter square. 1 millimeter square, okay? And there is no more simulation there. Just the measurements. So we have to be very careful. So the story I'm going to tell you is about that circuitry, which is the software radio circuitry. So basically, we have our voltage sample, fully analog. We are performing an analog Fourier transform. Fourier transform, that means spectrum. I have the spectrum in my hand with some voltage samples. Each voltage samples represent a part of the spectrum. Very easy. And if I want to address GSM or Wi-Fi, I have just to choose the right voltage samples that address that standard. Very easy. Just to pick one voltage samples for the right standard among thousands. Okay? So this is what this algorithm is doing. And when I have that sample among thousands, I have it in my hand, I can convert it into digital. Okay, so it's discretization again. But when I have only one among thousands, the frequency is very low. I have all my time to choose that voltage sample and I have all my time to convert it. That means that if the frequency is low but the resolution is still high, the power consumption of the ADC will be very low. That means that the technological bottleneck doesn't exist anymore. Okay, so this is another view to see how that decimation is performed. I have my spectrum into analog. Okay. C'est peut-être du français pour vous. Hein? That means in English it's maybe Chinese for you. Okay. Don't worry. So this is the validation of the ID. Okay? First step. Second step. That was to propose an architecture, an algorithm. Maybe you know the butterfly algorithm to perform a fast Fourier transform. So we have decided to choose that algorithm. So these figures. So I have my architecture right now. I have decided what I'm going to do in that architecture. And I propose that 3 stages. In each stages, I can detail all the parts of the architecture. Quite easy in VHDLMS, I can describe everything. And then I simulate all of that. Do I respect what a software radio chip should do? This is the question. So we've designed that chip, which is called size 64. I'm not a very good father. I don't know many names, so it's called size only. And I'm going to see if it's okay with the simulation. Next step. Oh, there is, yes. So, as it is a very complex circuit, I first work on very small building blocks, as you can see here. You can recognize at the schematic level the resistor here, the transistor here, the capacitor. Okay? When I put it all together, I launch my simulator and say, okay, it does that thing. Are you okay? Yeah, I'm okay. That's fine. That's what I want. Okay. So let's go further and further. Okay, okay. So this part is validated. The behavior is good. The schematic is good. So now I can draw my layout, you know, where all the circuitry is, where is the transistor, where is a resistor. So I've done that thing for all the circuitry. When I do very small building block, I can assemble it all together and make a huge circuitry. This is the small building blocks we've seen before. Here it's all in one big circuitry. And I still continue to validate the behavior of the circuitry. So here it's okay. I check the power consumption just to respect it. This is quite high here. I have to work a little bit more. So this is another part of the circuitry with other transistors, resistor. I make it together. I can draw the layout. Okay, this is another part. I make some simulations. That's okay for me. That's okay for the computer. That's okay for the guy who is going to pay for the circuit. Okay. So I respect all the specifications. I draw the layout. Okay. And I can see, oh no, the power consumption is not good. I have to work again. Okay. You see that after for the B version of the circuit. So what we were able to do in that circuitry, just to sum up, just to create 3 analog, and I say again analog operation, which are the delay, add and wait operation. Those 3 operations are able to do a fast Fourier transform. There is always a digital part to synchronize all that analog operation. Your job is not dead. Don't worry. Okay, so with 3 operations, I can create the first software radio chip. I told you there is a full simulation, each step. This is a full simulation of that circuitry. Only me can say that's okay. You agree? Okay, that's fine. Let's go further. This is a full chip. So we must say that the colors are very beautiful, isn't it? Nice colors. Okay, that chip, the area is 1.44 millimeter square. The cost is 50,000 reals. Wow. It was performed in the 65 nanometer CMOS technology, very small technology. As it is a demonstrator, it's not the 0 to 5 gigahertz software radio chip, but only the 0 to 500 megahertz. We'll see that for the B version. Okay, so I perform just sending all that to be fabricated. I perform a last simulation just to be sure that everything is okay. But that simulation is called a post-layout simulation. Post-layout, why? Because it's done after the layout. It includes all the parasitics effects. Just see, you have a metal layer like this, a metal layer like that. 2 metal layers equal 1 capacitor. So you have capacitors everywhere you didn't want in your circuitry. Metal is resistive. Resistor plus capacitor equal low pass filter. And low pass filter reduce the frequency. So I have just to check that. It was okay for me. It worked. Okay, so this is the applications of that circuitry. That means if I have a software radio chip, I can receive 2 standards at a time, maybe 3, 4. Okay, and we were able to see that if we read directly in the spectrum, you can demodulate the signals. Those are 2 applications. This is an interesting part. So this is my 2 childs. I present you Luca Testa and Saspapa. I have played on words in French, so si vous parlez français, vous aurez compris. So we have received that chip. I have to sell my car. Okay. This is the power alimentation here, the waveform generator, and the oscilloscope. 3 cars, 1 bicycle. No price, huh? Let's focus on the circuit. So this is a PCB. I have some switches to address the digital words to reconfigure my chip. My chip is here at the center in that small box. We'll see it right now. I've made a photography of my child. So it's 1,200 microns. The colors are not that good when it's fabricated. I prefer the previous one. So let's see the measurements. to sum up, we have three kinds of modulation. The phase modulation, the frequency modulation, the amplitude modulation. So I have tested my circuitry with those three modulations, and if it works for those three modulations, I can say it can work for any kind of modulation. Okay? So the very first one is a BPSK. That means that I have a phase shift of 180 degrees to encode a 0 or a 1. At the output of my circuitry, directly, the two levels, the high level, the low level. So we can see directly the 0 and the 1. This is software, but there is no ADC. It's hardware. Fun. Okay, another modulation scheme, which is a frequency modulation. Here we can recognize still the 0 and the 1, and the AS key. We can recover directly the envelope of any signal from 0 to 5 GHz. That circuit is able to demodulate any signal fully analog. And of course, as I told about concurrent reception, I can receive two signals at a time. So this is just measurements to validate that. I am close to the end. Wow. So, to conclude, just to say that Bordeaux Integrated Circuit Design Team has started investigations on software radio 6 years ago, and we have done one of the first ADC compliant intermediate frequency, so for software-defined radio, thanks to Professor Mariano, and designed the first software radio chip in the world, thanks to me. No, and the team, of course, it's a teamwork. But before the University of Berkeley, USA. We are very proud of that. Oh yeah. So, analog is not yet dead, as you can see here, because RF sampling architectures are coming back. It opens new research horizon, and of course, a lot of money if you want to be a researcher, no a designer, but a lot of fun if you want to be a researcher. And of course, to conclude that talk, I welcome you to come at Bordeaux if you want to work with us to be a researcher. Brazilians are still welcome to work with us. Thank you very much. If you have questions, yes. Wait. Je sais pas si vous...
Although it makes sampling on frequency modulation, which is the maximum limit of sampling per second?
Excellent question. So, because you have some jitter problem if you want to sample a signal, and at RF frequency, this is always a kind of trade-off in time. I mean, let's say some figures. I mean that till 5 GHz, it's easy. It's easy. We can control physical things. After that, I mean, from 5 GHz till 10 GHz, it becomes very hard. And this is another part we are working on. We are working on very reliable samplers, because that jitter effect becomes very dangerous from 5 to 10 GHz and very preeminent. So we have to work on very quick samplers. That means that at a time catch the voltage samples without that jitter effect. The jitter effect comes from the clock, comes from everything. So we have to think about that.
Nowadays, commercially used, which frequency, which text of sampling?
Sorry?
Is it? Nowadays, with commercial use.
I don't have that figures, but I think till 5 GHz, that's okay. After that, I don't know. To respect, that quality of sampling.
I designed some products that used wireless communication, and a very hard part of the design was to match the impedance of the output of my transmitter to the antenna and vice versa, and to make the antenna to work in the little broadband that I need to work. What's your vision about to make such a very high broadband to match those?
This is a very good question again. Wow. You want all to be researcher at Bordeaux? We are working on that also. And we have two ways to investigate. The first one is not to be at 50 ohm necessarily. I mean that your antenna is 50 ohm, the LNA is 50 ohm, things like that. Let's say we want to match the impedance, whatever it is 50 ohm or not, between all the elements. We're working on that. The other idea is to, I must say, enhance all the system together. That means that I have a very wide band I want to address. This is quite impossible, of course, but with very poor specifications, I must say. So, but if I have poor specification with very wide band, I can just listen where are the standards. And if I want to focus on one, I'm going to improve the specification of the LNA of the antennae at that time. That means all the system is smart and is going to adapt itself just to focus on one standard. Poor for everything, very good just for one thing. So this is an enhanced system. And maybe it's maybe a dream. In the future, we are still able to dream that we will have some very wideband, very good systems. I don't know. But we work on that just to make some very smart systems. And we are working on connective radio systems just to play smartly on that. So.
Okay. Thank you.
Another question?
I had two good questions. That's fine.
I have one. So in a system using the SASP, what's the expected specification for an ADC after the SASP?
I said that in the presentation, no? The specification for that ADC is a very low frequency ADC, no more than 1 megahertz of sampling rate, sampling frequency, but the resolution is still here, so it's always 16 or 70 bits.
Okay.
No more. And it's very low
the
power.
The same effective number of bits, so with sampling frequency reduced.
Yes, reduced
from
to
10 gigahertz to...
We were at 10 gigahertz to 1 megahertz, no more.
Okay.
I'm a good seller.
Yeah. Other question? Thank you very much again, Dr. Rivet, for coming here and share your knowledge with us. It's a pleasure for us to have you here, and you are welcome to Curitiba.
And
always welcome.
Welcome to Bordeaux. Thank you.
Thank you again.